Hello and welcome. My name is Raja. I'm heading the Developer Acceleration team for APJ. My co-presenter is Kenneth Ham. He is the Chief Technology Officer for Handshakes. Today, Kenneth and I will share our thoughts on managing software complexity and some critical best practices. Now, if you are a developer or a leader in software engineering, you may have some notion of software complexity already. To start with, let's look at some data points on how critical it is to manage software complexity actively at every stage of development. Following that, let's look at some mathematical ways of quantifying complexity. But more importantly, let's develop an intuition on this subject. Thirdly, let's look at some best practices to arrest the explosion of software complexity. The scope here is about accidental complexity, which is caused by unintentional, sometimes intentional, poor design choices that we often make. From here, I will hand it over to Kenneth to dive deep into a specific scenario where we applied these best practices and share what we learned from it. Now, let's dive into the data on why it's critical to manage software complexity. Now, this study talks about the startling amount of time developers spend in anti-work. Anti-work refers to the firefighting that happens due to quality and resiliency issues in production systems. I have seen this in the customers that I engage and have personally experienced it in my previous work lives too. One of the important root causes for this is the technical depths that were introduced because of unmanaged accidental complexity way ahead in the development lifecycle. Now, this anti-work further impacts businesses heavily with longer release cycles, as most time is spent in firefighting, as we saw. This also leads to very high costs due to operational overheads. The worst is the poor customer experiences resulting in loss of trust. And these are very, very critical business impacts. Another set of compelling data points come from the CIO risk ratings on major IT investments by the US government. You would see that 64% of the systems were rated to fail to either launch in time or were not able to deliver the business value in 2021. The same risk rating in 2009 was at 65%. Now, isn't that strange? There is not much improvement in the last 10 years. Even though we had DevOps revolution that happened in between, cloud adoption has been increasing during this period, and yet, something critical is missing. We will look at a possible explanation to this in this talk later. Another staggering number is the cost of worldwide IT failures due to unmanaged complexity again. It was estimated to be in the range of trillions per year. And this is bigger than the GDPs of a lot of countries. Such is the magnitude of the problem that we need to address. Now, if you are a head of engineering, I recommend you to estimate the annual cost of firefighting and the IT failures if you have not done so. This is just to quantify the urgency of this problem. So with that understanding of how critical this problem is, let's now shift to developing an intuition of complexity. Like good architects, we are going to zoom into a source code level example and build up our understanding of complexity. And then we will zoom out to discuss the same from the large-scale systems perspective. Now, let's look at this snippet of code. You may pause the video here if you like. However small this snippet is, you might find that it is harder to read and comprehend in the beginning. After a while, you would understand that it is about a certain billing logic. The for loop at line 5 iterates through all the usage records. Line number 6 filters the records that needs to be charged. Lines 7 to 10 applies some tier-based charging. Now, it all comes to us slowly. Right? Now, let's look at a better version of the same code snippet. At the first look, you would find that the code on the right-hand side is more readable. Lines 7 to 10 does filtering, applies the tier-based pricing, and sums it all in the end. And the actual logic for each of these operations are coded in lines 3 to 5. Now, instinctively, this is more readable. But what really made this code more readable? Shall we wear our designer's hat and reason this out? So we can see that a number of design principles are followed, which contributed to this high readability. Lines 7 to 10 are composable, making it easier to add additional processing if needed. Here, we are only dealing with composing the operations, but not about the actual logic of the operations themselves. That logic is segregated to lines 3 to 5 above. Each function there does only one thing and only one thing very well. They can be externalized, developed, tested, and deployed independently without any ripple impact to the rest of the program. In short, what this has brought in is the golden purpose of least cost to change and extend in the future. This is the core objective of any design. Wait, but we are all about quantifying and measuring everything. Is there a way to mathematically quantify this commonsensical conclusion we have reached? What are the metrics? And if we have to use a tool, would the tool agree with our commonsensical conclusion? Now, I have the same two snippets coded here. Here is the first version of the code, and here is the improved readable version of the same code. Let us run a profiler on this. Now I have run it. Let's look at the report. The tool says the maintainability of the first version of the code is 61%. Now, is that enough? Perhaps no. But the maintainability of the improved version of the code is 100%. That is very good. This matches with our commonsensical conclusion also. So what contributed to this maintainability score can be found below. One of the important metrics is the cyclomatic code complexity. It is 4 for the poor version and 2 for the improved version, twice the better. Now, there are different takes on computing cyclomatic complexity, but a common method is to transduce the code into a graph of branches and nodes that represents the control flow. You can see that the if statement in line number 6 is represented as a node with 2 edges in the graph. There is a formula using which the cyclomatic complexity is calculated to be 4. The important takeaway from here is that the control flows and decision structures in your code can be represented and visualized as a graph of edges and nodes. That is the takeaway. Now, let's zoom out and look at the entire complex system as a whole. Like the real world, the world of software is also fractal in nature. The same notion of nodes and edges apply here also. In here, the nodes are the components, and the edges are how the components interact with each other. I have an opinionated view of quantifying complexity in large-scale systems, as in the formula below. It is the sum of cyclomatic complexity of all the components multiplied by the number of afferent and efferent edges they have. Keeping the formula aside, let's focus on what it really conveys. From the formula, we can derive that software complexity is directly proportional to the number of edges and the number of nodes. This notion is very simplified, of course, but it captures the full essence. If a component has a large number of edges, this reflects very high dependency, also called as tight coupling. If the system has too many accidental components to implement the same functionality, this symptom is called as low cohesion. Both these lead to very high accidental complexity, which results in very poor maintainability. Let's take a practical example. I have a certain system implemented using components calling each other in a point-to-point manner in the left. You can notice the large number of edges in that topology. This system is essentially very complex due to the temporal coupling that these components have on each other. There are also other tight coupling aspects with respect to protocols, message formats, failure handling, etc. Let us assume that the same functionality can be implemented in an asynchronous, event-driven manner. That topology is presented on the right side. We can straightaway observe the reduced number of edges in the right. And these edges are barely essential, leaving no room for any accidental complexity. We all know how the event-driven architectures fix the failure modes of tightly coupled, synchronously communicating systems. This proves the point that reducing the accidental edges and components results in reduced complexity. Now, let's summarize all the arguments here. As we reduce the number of edges, we are reducing the dependencies. This is the loose coupling design principle that reduces the system complexity. Reducing the number of accidental components is a second design principle called high cohesion. We can derive that high cohesion and loose coupling leads to reduced complexity. Now, we always design systems with a lot of unknowns at any given time. That is a very hard constraint. So, the most desired benefit we want is that the design makes the future changes and additions least expensive. We achieve the low cost of future changes if we have reduced the complexity. Now, I want to reiterate our conclusions by quoting two of my favorite thought leaders in computing science. Kernighan points exactly to the subject matter we are discussing, that controlling complexity is the essence of programming. This inspired me to dive deeper into this subject. And Grady Booch says that the essence of design is to minimize the cost of change, all in great alignment with what we are talking. Now, let's look at some of the top practices in managing complexity. You might have come across this famous quote from Dave Thomas: big design upfront is dumb, no design upfront is even dumber. There is a lot of debate happening on this subject now. Design is to minimize the cost of future changes. But if big design is wrong and no design is also wrong, what is the answer then? In my opinionated view, it's not about big design or no design. It is about quality design. And quality here is a factor of reduced complexity. We are going to do the design until we are convinced that we have done sufficiently enough to reduce the complexity to the minimum. How do we know we have done enough? For that, we are going to assemble some best practices and litmus tests into a design method specifically focused on reducing the complexity. Now, I'm going to use two principles in this new method. First is decentralize wherever possible. That is, to decompose the architecture into multiple independent boundaries to reduce the blast radius of design choices. Number two, reduce the architectural feedback loop. We don't want to wait until the full system is built to measure the complexity. We would use litmus tests and fitness functions to constantly reduce complexity at every stage, shifting this intention to the left. This is the baseline no design upfront scenario. We go from functional requirements into physical architecture straight. As you can see, there are no conscious steps in between to check the quality of the design. This probably is where complexity creeps in. without even we realizing it. Let's ponder on this deeply. Here is a recommended method. I call this Day1 Systems Design Method, or in short, Day1 SDM. I'm introducing two frugal steps before we get to the physical architecture. The first step is domain modeling, where we just model the business into multiple boundaries that are loosely coupled and highly independent. This is a crucial first step to reducing complexity. The next step is to dive into each of these boundaries and create the logical architecture. At this stage, we will use all the design patterns and best practices to keep the number of edges and components low. If done correctly, then physical architecture is just a mapping of logical system components into the right AWS services. The inputs to each of these steps are represented in pink, and the outputs are in orange color. Now, let's look at some next level details of each of these three steps. Domain-driven design by Eric Evans captures decades of wisdom in designing complex systems, and it laid the foundation for the microservices paradigm that we practice today. Event storming is a fun technique to apply domain-driven design in a gamified manner. With some simple steps, you can arrive at a powerful domain model that IT and business can use to communicate with each other like never before. And one of the important outcomes from here are the bounded contexts, which are loosely coupled boundaries within which the model components are highly consistent and extremely cohesive. This top-level decomposition is the first step to reduce the system's complexity. This prevents the eventual big ball of mud syndrome and limits the blast radius of any design choices. There are enough books and guides available on these. You may, of course, reach out to us also. Now, we are going to take the pure domain model from the previous step and apply the non-functional requirements to it. By doing so, we will discover the requirements like distributed transaction management, caching, etc. We design the necessary system components for these by referring to a library of design patterns and other solutions already existing. I have my own reference library of solutions that I reuse. This has an opinionated taxonomy. There is a list of design patterns with descriptions and reference links available there. There are other building blocks like system design foundations, algorithms, data structures, essential mathematical constructs, etc. These patterns and solutions are built with complexity reduction in mind. These abstractions further minimize any accidental complexity that may potentially creep in. I would want to insist that at this point in time, we need to document the architecture decisions. Documenting architecture decision records is a forcing function for us to consciously reduce complexity. I also recommend you to develop and use your own complexity storming practice. That is to develop a library of questions to challenge a logical design towards minimizing the number of edges and nodes. We will see some examples of this later. Now, all that is left is to map the logical architecture components to respective AWS services. This should be easy. The principles from well-architected framework further helps to design the systems predictably with minimal complexity. So with that discussion on the method, I will invite Kenneth to walk us through how this Day1 SDM method was put into practical use to reduce complexity and achieve the desired outcomes in our joint engagement.
Thank you very much, Raja, for the introduction, and hello, everybody. As Raja mentioned, my name is Kenneth, and I'm the Chief Technology Officer for Handshakes. Handshakes is a data and AI company. We empower clients by delivering meaningful insights harnessed from reliable data, enabling them to make safer and more informed decisions. However, we face a challenge with graph processing capability while loading more than 4 degrees of network connections. Think of us as Facebook or LinkedIn for corporates. If we continue empowering our clients with accurate and actionable insights, this problem needs solving. We were determined to overcome this challenge to optimize our graph processing capability. We partner with AWS to find a solution enabling us to do just that without compromising speed or accuracy. Our collaboration with the AWS Developer Acceleration Team aimed at achieving 2 objectives: technology enablers and human enablers. The first objective focused on technology enablers, which involve modernizing the core application to increase our release frequency and market velocity. As a result of this modernization, we could eliminate technical debts. The second objective was on human enablers and capabilities, which involved transforming and modernizing our engineering teams. Through our partnership with DevX, our engineering teams was able to adopt modern application development best practices. This helped them confidently develop codes and inculcate a habit of prioritizing best practices. As a result, knowledge transfer was achieved, enabling our engineering teams to operate independently even after the engagement. Our approach to solving the problem at hand centered on engaging our most senior engineering team members. Their technical expertise, depth, and extensive experience proved invaluable in addressing the underlying issue effectively. By tapping into their wealth of knowledge and experience, we could approach the problem from a more informed and strategic perspective, allowing us to identify and implement effective and efficient solutions. The team's collaborative efforts also resulted in a more streamlined and coordinated approach, ensuring all parties involved were on the same page and working towards the same goal. Now, let us dive into the details of the system design scenario. We followed the Day1 SDM method introduced earlier, and the first step was domain modeling. Using event storming techniques, we applied domain-driven design principles to decompose our application into highly cohesive and loosely coupled microservices. With AWS, we co-developed litmus tests to validate the correctness of our design and keep the complexity under control. The litmus tests cover the design dilemmas, like checking if we have overly decomposed our system into nanoservices. The tests combine a selected set of services to check if the solid principles were followed. For example, we combined Entity Explorer with combinations of other services and tested if the single responsibility principle was compliant. Another test was to validate if any future changes within one boundary do not negatively impact other parts of the system. You may contact us if you want to know more about these complexity storming techniques. We were able to narrow down the problem to this logical architecture. In this design, we have yet to map any AWS resources. DevX team's engagement allowed us to do just that by solving our business problem agnostic to cloud technologies. Our objective was to achieve a 99.99% availability while computing a 3-degree connection search in under 10 seconds. This is a benchmark against 10 million nodes and 50 million edge graph networks. The architectural decision the team had to make was either commercial off-the-shelf NoSQL graph databases or a custom graph engine built using an optimized breadth-first search algorithm. We iteratively performed complexity storming to minimize the number of edges in components in this system. For example, we adopted design principles and patterns like straggler and CQRS to simplify the design drastically compared to the existing system. As we dive a little deeper into the complexity benchmarks, we're looking at 4 factors for comparison: algorithmic complexity, cyclomatic complexity, cost of change, and performance. Algorithmic complexity measures how long an algorithm would take to complete given an input size. This tells us how long the code would take to compute and the number of variables allocated in memory, equivalent to time and space complexity. Cyclomatic complexity is a software metric used to indicate the complexity of a program. This tells us the complexity of the program correlating to the number of defects to reduce complexity, eventually reducing risk and eventually resulting in a lower cost of future change. Cost of change is the dollar value a project incurs if a business requirement is modified before or after delivery. Naturally, we want the cost of change to be as small as possible. This mandates that we keep the algorithmic and cyclomatic complexity to the minimum. These decisions must be made earlier to reduce waste in the development and save expensive testing and maintenance costs. This was the core objective of our logical modeling. Last, performance indicates a system's responsiveness to execute any action within a given time interval. This lead indicator helps us to understand if the 3 factors above are achieved. Software performance is the first interaction the user experiences, and the slightest performance degradation will in some cases result in a reputational risk, while in others, it might be negligible. The overall outlook of this table indicates that the custom graph engine using an optimized breadth-first search algorithm is the better option because of the enhanced performance with low complexity and risk compared to the commercial off-the-shelf products. The relative performances are here for 3 degrees, and in our benchmarking, once the number of network degrees increases, the alternative solution will exponentially increase in latency. Notably, the performance achieved using the custom graph solution is at 1.3 seconds compared to the commercial off-the-shelf products. The commercial off-the-shelf products were great. However, it requires numerous database tuning, optimizations, and efforts to achieve an optimal state compared to the custom graph solution, which we had maximum control over. The consideration from a business perspective in our scenario is 2 critical factors. The first is cost. The second is maintainability. From a cost perspective, a custom graph solution will require the cost of developers, running costs on the cloud, and the cost of future upgrades tightly coupled to a custom solution. This leads to the second point, maintainability. Maintenance costs to keep a custom solution stable will be a hefty investment. At this stage, with the complexity reduction achieved at the logical architecture design, we can map the logical architecture into AWS services. We designed the service in a stateless architecture designed for scale using containers and for easy maintenance. We applied AWS Well Architect framework to meet the non-functional requirements. In this demo, we've deployed the radial graph engine on AWS ECS cluster. We've deployed 2 ECS tasks as a baseline capacity for higher availability. Now, we will run the command to check the health of our ECS cluster. Next, we will execute the radial search using this command that points to the AWS load balancer endpoint. We can observe that the result took 48 seconds to retrieve 13.5 million records for a 6-degree radial search network connection. We've achieved our objectives of high availability, improved performance, and reduced software design complexity. The infusion of digital technology into our product helped us to do more with less. Our partnership with DevX has allowed our business to thrive with innovations and agility that the cloud enables. but also the ability to integrate with our existing technology investments. We can scale with demand, and moving to the cloud helped us to do just that, converting our spending from CAPEX to OPEX. The engagement with AWS DevX enabled our business to invest in quality design right from the start by reducing the complexity of the codes we write. We were able to achieve loosely coupled systems from a complex solution. Through the partnership with DevX, our engineering teams could leverage best practices like domain-driven design to solid design patterns and well-architected frameworks. Thank you for watching Raja and I share about tackling complexity at the heart of systems. We hope this session was engaging and insightful. We've covered a few topics from why we should manage software complexity, to what it is, to how to manage it, and eventually putting into perspective the partnership with Handshakes to tackle complexity at the heart of our systems. A big thank you, and we hope you enjoy the rest of the AWS Summit.
Thank you very much, Kenneth. We hope all of you watching this found the session insightful and motivates you to look at software complexity with critical importance. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Thank you again for attending, and we really appreciate your feedback so that we can get better understanding of the topics and services you would like to know more about. So please do take time to fill out our survey and let us know what you think.